G'day, I'm Daniel Fryer from the School of Mathematics and Physics at the University of Queensland. In this video, I'm going to talk to you about my research forecasting day-to-day psychiatric symptoms using digital phenotyping. Take a look at this diagram here. The phenotype of an individual is the set of observable characteristics that result from the interaction of the individual's genotype with their environment. So a subset of those interactions are going to be captured by smartphones. The idea with digital phenotyping is that we can use that data to understand more about the individual, since it constitutes a sort of a rich set of social and behavioral fingerprints. The term digital phenotyping was coined in 2015 by Jukka-Pekka Onola from the Harvard School of Public Health. And it's the moment-by-moment quantification of the individual level human phenotype in situ using data from smartphones and other personal devices. I want to pay attention to the "in" here in digital phenotyping because it's supposed to emphasize the dynamic nature of digital phenotyping. The idea is that it's not a static thing, it's moment by moment, and we're quantifying details about the individual in situ. So this here is my main research question. We seek to accurately forecast or predict the way that psychiatric symptoms are changing on a daily basis using data inferred from smartphone sensors. Okay, so here we mean data that's sensed passively. It includes data collected from the keyboard, the microphone, video, Bluetooth. Okay, these things give us information about social dynamics and voice samples. They also include GPS, giving spatial trajectories, and the accelerometer, giving mobility patterns like running, walking, or riding a bike. So we're not dealing, for example, with an actual conversation that the person is having and the content of the conversation. We're dealing with some inferences about the conversation, like the quality of the conversation. Is it argumentative? Is it generally a happy or friendly conversation? This is data with many features. Okay, so it traditionally leads to statistical issues due to sparsity. Intuitively, this is because with more dimensions, there are more ways for things to be separated. So, for example, how do we cluster individuals together when they have so many features and so many ways to appear different? We're not just dealing with a single moment in time or a few time points. We're talking about snapshots of sensor readings that are being taken in some cases every second. We're producing time series that describe continuous random processes. So there's an implied statistical modeling problem here. We seek to establish a de facto class of statistical models for dealing with this kind of high-dimensional and intensively longitudinal data. So here are the two most important papers for understanding the background of my research. The first one by Jukka-Pekka Onola and Scott L. Rausch coins the term digital phenotyping. An important quote from that paper is that as digital phenotyping matures, it seems likely that the intellectual challenge will shift from data collection to data analysis and modeling. The paper goes into technological origins and potential of the technology. Despite the excellent research contained in those key papers, there simply is no example in the literature of using a large, carefully labeled, high-quality, high-volume, longitudinal dataset to predict ongoing psychiatric prognoses. There's no demonstration of using digital phenotyping to achieve continuous long-term prediction and awareness of patient outcomes. The current procedure between the clinician and the patient is that the clinician will meet with the patient maybe once per month and that they'll get this cross-sectional view of the patient's life. So it's this non-ecological cross-sectional observation, and it's difficult to use that for forecasting. The idea is that we want to complement the work of a therapist by providing a continuous stream of longitudinal data and the associated inferences for between when the patient is actually able to make contact with the clinician. Mental illness is dynamic, so day-to-day presentations are in a constant state of flux and with between-patient heterogeneity that often breaches rigid diagnostic categories. So we want to take advantage of this heterogeneity so that we can do a sort of trans-diagnostic clustering, so we can get this precise clustering of patients, and that sort of bespoke clustering is a major goal of precision medicine. So this brings us to the real puzzle. These so-called digital phenotyping data have the potential to revolutionize psychiatry, but we face two obstacles. On the one hand, the methodology for forecasting psychiatric prognoses continuously from these data doesn't exist yet. Secondly, the conventional statistical methods for inferring causal mechanistic relationships are not suitable here. Here's our idea. We'll forecast individual patient symptom severity as indicated by daily patient survey results. The primary survey outcome to be forecasted is degree of patient functioning. Now, this is a discrete ordinal variable formed from an aggregation of reported indicators of difficulty completing daily tasks. The predictions will be made from a panel of activity logs and smartphone sensor readings. We expect that patients should be clustered transdiagnostically into groups that have distinct time and scale varying patterns of correlation between digital phenotype features and daily survey results. Now, this project actually involves 3 datasets. Now, the first of these is student life. It was created back in 2013 with a group of volunteer college students. The purpose of it in this project is to act as a sort of practice dataset. And in order to manipulate it, I've published a R package on CRAN and an associated bulletin in the Journal of Open Source Software. Secondly, the main dataset is currently being acquired in a large sample of psychiatric patients in psychiatric hospitals around Montreal in Canada with our partners over there. There is a sample size of 100 patients who've been diagnosed with schizophrenia, depression, or bipolar disorder who undergo a 4-hour clinical assessment before undergoing data collection for 100 days. During the study, they will give feedback in the form of daily surveys. Anticipating less than a 50% patient drop-off rate, the sample size of 5,000 patient days will be enough to provide good statistical power. However, the main obstacles expected are high dimensionality, data missingness within patients, variability in the quantity of data between patients, and variability in the frequency of missing data over time, both within and between patients. These obstacles make traditional time series analysis difficult, and they open the door instead to a number of state-of-the-art machine learning algorithms. In a final phase, the sample size will be able to grow to thousands because the app that is currently being used to collect the data in psychiatric patients will be made available to the public. This means that we will have an excellent platform for testing and further model development. It's known that any data generating process can actually be approximated to an arbitrary degree of accuracy using a mixture of experts model. An MOE model will also allow for clustering by digital phenotype with weighted degrees of patient membership for each cluster, determined by optimization of a gating network. Now, gating network is a neural subnetwork that has the role of determining which submodel is most appropriate for making predictions on a given patient. The probabilistic nature of mixture models will also allow data missingness to be handled, for example, via the use of an expectation maximization algorithm. So about this research, so what? Roughly 54% of Australians with mental health conditions don't actually access treatment, and that's roughly double the rate for people with other physical conditions. Suicide is the leading cause of death in Australia for people aged 25 to 44. Instead of waiting for this major psychiatric crisis leading to potential hospitalization and then discharge and then often high readmission rates, we have the potential to provide predictions on when to allow patients, caregivers, or loved ones, let them know when a patient with chronic psychosis is about to decompensate. This research will provide the modeling framework required to build the first generation of tools providing continuous dynamic prognoses for psychiatric patients, allowing clinicians to provide life-saving, cost-saving interventions and care when needed. This is going to give incredible economic and human benefit, and my research is part of a larger project with funding to develop similar tools. This is the bottom line. What's new here? The novelty lies at the intersection of 3 important achievements. First, there's this one-of-a-kind, carefully labelled digital phenotyping dataset on psychiatric patients. That's the main dataset. Second of all, we're acting as pioneers for new methods that will be used to help therapists continuously predict daily symptoms. Third, we're achieving this valuable and natural, precise, data-driven clustering of patients, which contrasts with classical reliance on rigid diagnostic categories. Searching through the literature, we were unable to uncover any demonstration of using smartphone digital phenotyping data in order to achieve continuous ongoing prognosis of psychiatric symptoms. There are no coherent proposed frameworks for modeling this type of data arising in smartphone neuroinformatics. We believe that we're the first to propose a research plan that thoroughly explores the deficits in the literature. The main dataset is expected to be available in January 2020, that's a month from now. This is part of a larger project involving collaboration between clinicians in industry and statisticians and neuroscientists in academia. The data process already has ethics approval, and the larger project is well funded. Thanks for watching.